In 1994, a comet hit Jupiter with a force of 300 times every nuclear weapon humanity has ever built. All of them. At once. Jupiter didn't notice. Before we talk about Jupiter, we need to talk about a woman named Carolyn Shoemaker. In 1993, Carolyn was photographing the night sky at Palomar Observatory in California. Something she had done thousands of times, scanning the darkness for faint, moving dots that might be comets or asteroids. She was 65 years old. She had discovered more comets than any other person in human history. She was methodical, patient, precise. She had spent decades training herself to see what other people missed. And on the night of March 24th, she noticed something wrong. On a photographic plate of the sky near Jupiter, there was a smear. Not a dot, the way a comet normally appears. A smear, an elongated streak of light, like someone had pressed a thumb across the image. She called her husband, Gene, and their colleague, David Levy. They looked. They agreed. This had never been photographed before. What Carolyn Shoemaker had found was the shattered remains of a comet that had passed too close to Jupiter the year before, been captured by Jupiter's gravity, been torn apart by Jupiter's tidal forces into 21 separate fragments, and was now, all 21 pieces, aimed directly at Jupiter on a collision course that would play out in July 1994. Astronomers immediately understood. They calculated the orbits. They confirmed the impacts. And then they did something that had never been done before in human history. They prepared to watch a catastrophic collision in another world happen on a schedule they could predict, with instruments powerful enough to record every detail. For the first time, humanity could watch the solar system be violent without being the victim. The impacts began on July 16, 1994. Fragment A hit first, moving at 60 kilometers per second. It struck Jupiter's southern hemisphere and exploded with the energy of 225,000 nuclear weapons detonated simultaneously. It left a dark scar in Jupiter's atmosphere the size of Earth, visible through amateur telescopes from our planet's surface. Then fragment B hit, then C, then D. Over 6 days, all 21 fragments struck Jupiter in sequence, like a drum roll played by the solar system itself. By the end, the impact scars on Jupiter's southern hemisphere, laid side by side, covered an area larger than the entire surface of Earth. The total energy released was approximately 300 times the combined yield of every nuclear weapon ever built by every nation in human history. And Carolyn Shoemaker sat at Palomar Observatory and watched every impact through her telescope, crying. Not because it was terrible, because it was real. Because she had spent decades learning to see what other people missed. And this catastrophic, violent, impossible event was what that life of looking had led her to. She was watching a planet absorb a disaster that would have ended us. She knew it, and she wept. Her husband, Gene, co-discoverer of the comet, the man who had stood beside her at that telescope, did not survive long enough to see what the discovery became. He died in a car accident in 1997, 3 years after the impacts. He never saw the Galileo spacecraft's detailed data from Europa. He never saw the plumes. He never saw what his co-discovery helped illuminate about where life might exist in this solar system. He gave everything to understanding what Jupiter is. Jupiter did not notice. This is where we begin. not with Jupiter's size, not with its storms or rings or magnetic field. We begin with two people who spent their lives learning to see. What they saw when they finally looked at Jupiter clearly. Jupiter is not a planet, not in the way we normally use that word. A place, a destination, a world to catalogue. Jupiter is a condition. The condition under which everything in this solar system was possible. The condition under which Earth formed, oceans filled, life began, and you exist right now, reading this, breathing, alive. Jupiter is the reason there is a reason for anything here. And it has never once thought about you. We need to establish scale. And I need to be honest with you up front. Your brain will not be able to hold what I am about to say. Not really. You will process the numbers. You will nod. You will think you understand. You will not. No human mind can truly comprehend the scale of Jupiter, because human minds evolved to track prey across open ground. And the largest thing our intuition was built to handle is something we can walk around. Jupiter cannot be walked around. It can only be approached, like a coastline you can see, but never reach. But let us try. Take a basketball. Put it on the table in front of you. Now, take a single peppercorn from a pepper grinder and place it next to the basketball. The basketball is Jupiter. Peppercorn is Earth. Look at the peppercorn. Really look at it. Every mountain range on Earth. Every ocean. Every city ever built. Every person who has ever lived. Every philosopher. Every general. Every scientist. Every child. Every language ever spoken. Every book ever written. Every song ever sung. The entire recorded history of our species. Inside the peppercorn. And the basketball, Jupiter, sitting next to it, unchanged, unmoved, not even aware of the comparison. Now, you could fit 1,321 peppercorn Earths inside that basketball. Every continent, every ocean, every living thing, 1,321 times over. And Jupiter would be unaffected. Not fuller, not heavier in any meaningful sense. Just Jupiter, being what it has always been. The great red spot, Jupiter's iconic storm, has been spinning for at least 360 years. The last time it didn't exist, Newton was still alive, and right now we are the generation watching it die. But size is not the most important thing about Jupiter. Mass is, and mass is not the same as size. Mass is the amount of stuff. Jupiter has 318 times the mass of Earth. That mass generates gravity, and that gravity reaches not just to Jupiter's own moons, but across the entire solar system. Jupiter controls the asteroid belt. It shaped the orbital evolution of Mars, Earth, and Venus as they formed. In the early solar system, Jupiter was so massive, so quickly, that it began physically migrating, actually moving through the young solar system, consuming and scattering and reshaping everything in its path, before Saturn's gravity stopped it and pulled it back. Jupiter moved. A basketball moving through a room full of peppercorns, rearranging everything in its path. We are built from the peppercorns it did not consume. We are the crumbs that fell off the table of the real meal. And Jupiter rotates in 9 hours and 56 minutes. Less than 10 hours. For something this large, that is violent. The equatorial edge of Jupiter moves at roughly 45,000 kilometers per hour. So fast that Jupiter has physically deformed itself stretched at the equator, flattened at the poles. A planet that has distorted its own shape through the sheer force of its own spinning. You can see it in photographs. Jupiter looks wrong. It looks squashed. It looks like something spinning so fast it is trying to tear itself apart, and has not quite managed it yet. This is not a planet in the way we mean when we say the word planet. This is the dominant object in this solar system after the Sun. There is no door into Jupiter, no hatch, no surface, no altitude where things become survivable and the journey becomes possible. Jupiter is gas and liquid all the way down, and down goes a very long way. The upper cloud tops are cold, minus 145 degrees Celsius. The ammonia ice clouds here are the ones we photograph, the pale cream zones and the reddish-brown belts that make Jupiter look like a painting. Cold, thin, almost delicate at this altitude. Keep descending. The ammonia clouds give way to ammonium hydrosulfide, a compound that does not exist in any meaningful quantity on Earth. The clouds here are brown and orange and wrong-smelling in a way no human language has a word for, because no human has ever smelled them and returned to describe it. It is getting hotter. The pressure is building, hundreds of times what you feel at Earth's surface. The light from above is dimming from pale gold to amber to brown to nothing. Below that, water clouds. A water cloud layer deep in Jupiter's atmosphere, where temperatures approach what we experience on Earth's surface. This is where Jupiter's lightning is born. In water clouds, exactly as on Earth, but in storms thousands of kilometers wide. Jupiter's lightning has been detected by every spacecraft that has passed close enough to listen. Voyager, Galileo, Juno, each detected radio bursts, electromagnetic screams from bolts of electricity firing through water clouds deep in the atmosphere. The energy in each strike rivals the most powerful lightning ever recorded on Earth, and they fire by the thousands. Every hour, everywhere. Jupiter is never quiet, even in its depths. And still you descend. The light is gone, completely. You are deep in something that has no name in human experience. A supercritical fluid, neither gas nor liquid, where the distinction between states of matter has dissolved under pressures millions of times greater than what you feel right now. The temperature is thousands of degrees. You have left behind every reference point your body was built to interpret. There is no up, no down, no surface, no sky, just increasing heat and increasing pressure and increasing darkness forever. And then, somewhere between 20,000 and 30,000 kilometers below the cloud tops, hydrogen, the simplest, lightest, most ordinary element in the universe, does something that has no parallel in everyday human experience. It becomes a metal. Under pressures this extreme, the electrons that orbit hydrogen atoms are squeezed out of their orbits. They cannot remain attached. They break free and begin flowing between atoms, the way electrons flow through copper wire. Hydrogen stops being a gas, stops being a liquid, and becomes an electrical conductor. Liquid metallic hydrogen. A substance so exotic that for decades after its theoretical prediction, we could not create it in any laboratory on Earth. We can now produce it for microseconds in extreme pressure experiments. Jupiter has an ocean of it, thousands of kilometers thick, conducting electricity on a planetary scale, carrying currents that wrap around the entire planet, driven by Jupiter's rotation and its enormous internal heat. Those currents are what generate Jupiter's magnetic field. Earth's magnetic field extends roughly 60,000 kilometers on the sunward side. It deflects the solar wind. It keeps our atmosphere from being slowly stripped away. It makes our planet habitable. We consider it essential. Jupiter's magnetic field extends 650 million kilometers on the side, facing away from the sun. If you could see it with your naked eye from Earth, it would appear 3 times the size of the full moon in the night sky. Every night, an invisible empire reaching past the orbit of Saturn. And what Jupiter does with that magnetic field is build a trap. The radiation belts around Jupiter, zones where charged particles are captured and accelerated by magnetic field lines, are the most lethal electromagnetic environment we have ever encountered in the solar system. A human being in those belts without extraordinary shielding would receive a fatal radiation dose in minutes. A standard spacecraft would have its electronics destroyed in hours. Even the Juno spacecraft, built specifically to orbit Jupiter with a radiation-hardened titanium vault protecting its instruments, plans every orbit carefully to minimize time in the worst zones. Jupiter has surrounded itself with an empire of death. And in the center of that empire, beneath the clouds, beneath the metallic ocean, at the very core, something is dissolving. Data from the Juno spacecraft has revealed that Jupiter's core is not the compact, solid ball scientists assumed. It is enormous, diffuse. It extends over a region perhaps half the radius of the planet. A fuzzy, gradual blending of rock and metal and compressed hydrogen, as if the core has been slowly dissolving into its own atmosphere for billions of years. A heart that is melting, coming apart in slow motion over timescales that make all of human history invisible. Jupiter generates twice as much heat as it receives from the sun. It is burning its own reserves, the remnant energy of its formation, the heat of helium droplets condensing and falling through the metallic hydrogen like rain made of metal. It is running down, spending ancient savings, cooled by degrees so small they cannot be measured on human timescales. Jupiter is the most powerful thing in this solar system, and it has been dying since the day it was born. Robert Hooke was 29 years old in 1664 when he pointed his telescope at Jupiter and sketched something in the southern hemisphere. A spot, reddish, distinct. He noted it and moved on. He was one of the most brilliant and difficult men of the 17th century and had other things to pursue. He had no way of knowing that the thing he drew in 1664 would still be there 360 years later. The Great Red Spot was the largest storm in the solar system, an anticyclone, a high-pressure system rotating in the opposite direction to a hurricane, sustained between 2 counter-flowing jet streams, held in place by Jupiter's atmospheric dynamics, the way a ball bearing is locked between 2 rotating gears. It has been spinning since before the United States existed, since before the Industrial Revolution, since before Newton published his laws of motion, since before Hooke himself was born. At its peak, estimates suggest it stretched 40,000 kilometers across, wider than 3 Earths placed side by side. A single storm, with its own horizon. If you stood at its edge and looked toward its center, the center would be below the curve of the planet. You could not see across it. It was not just larger than a planet. It was large enough to have its own geography, and it was red. a deep, shifting gradient of salmon and rust and brick and cream. The red comes from complex organic molecules, compounds involving sulfur and phosphorus, dredged up from deeper in the atmosphere by the storm's circulation, and chemically altered by ultraviolet radiation from the sun. We have been studying it for 3.5 centuries. We are still not completely certain what makes it that specific shade of red. There is something honest about that, something that keeps planetary scientists humble. The Voyager spacecraft photographed it in detail in 1979. The Cassini spacecraft imaged it in 2000 on its way to Saturn. Galileo studied it. Juno has flown over it. Every generation of spacecraft, every generation of astronomers, every generation of curious humans with telescopes, they all found the great red spot where it was supposed to be, exactly where Hooke had drawn it, spinning. And then, quietly, it began to end. Through the 1990s, through the 2000s, through the 2010s, the storm contracted. Measurably, steadily, without drama. By 2024, it had shrunk to roughly 13,000 kilometers across, 1 Earth diameter. Still a storm that would cover the continental United States 3 times over. But compared to what it was, compared to what it has been for 360 years, it is a shadow of itself. It is not just shrinking. It is losing its shape. It was a smooth, stable oval for most of its recorded history, rotating with the certainty of something that has done the same thing for centuries. Now it is rounder. Pieces are breaking off the edges. Smaller vortices tear away and spin off into the surrounding atmosphere. The storm is fraying. The great red spot is dying, and we are the generation watching it happen. Amy Simon, a planetary scientist at NASA's Goddard Space Flight Center, who has spent decades studying Jupiter's atmosphere, has dedicated a significant part of her career to tracking the great red spot's evolution. She has watched, data point by data point, season by season, as the storm she built her expertise around has contracted. She measures it. She publishes papers about it. She does science about it. And underneath the science, in the quiet between calculations, she is watching something she loves being lost. Every scientist who has ever studied Jupiter professionally grew up with the great red spot as a permanent feature. It was assumed, in the deep unspoken way that assumptions work, to be essentially eternal. A fixture, a landmark, the first thing anyone showed you when they showed you Jupiter. And now the people who have spent their lives studying it are watching it go. When it is finally gone, in a century, perhaps 2, Jupiter will look different. The southern hemisphere will be emptier. The face of the planet will have changed. And every photograph ever taken of Jupiter, every drawing since the 17th century, every image on every textbook and poster, all of it will contain something that no longer exists. Robert Hooke drew it at 29 and died at 67 without suspecting it would outlast empires. We will be the generation that watches it end. And Jupiter will not notice. Jupiter has 95 confirmed moons, a civilization of worlds ranging from tiny captured rocks barely a kilometer across to bodies larger than planets. Each one is a different answer to the question of what Jupiter's gravity can do to something caught in its orbit. Some of those answers are extraordinary. Io is the most volcanically active world in the solar system. not in the inner solar system, not among the rocky planets, anywhere. On a moon roughly the size of our own moon, orbiting Jupiter at 422,000 kilometers, there are 400 active volcanoes. Not dormant, not periodically active. Active, erupting as you read this. The reason is gravity. Io is locked in a gravitational resonance with Europa and Ganymede. For every 4 orbits Io completes, Europa completes 2, and Ganymede completes 1. This means the gravitational tugs from Jupiter and the other moons never settle into a stable pattern. Io is perpetually squeezed and stretched, kneaded by competing gravitational fields, its entire body flexing with every orbit. That flexing generates friction. Friction generates heat, and that heat vents through hundreds of volcanic fissures in rivers of lava and sulfur plumes that reach hundreds of kilometers into space. Pele, one of Io's largest volcanic regions, creates a plume 300 kilometers high and leaves a sulfur frost deposit covering an area larger than Alaska. Loki Patera is a lava lake larger than the state of Oregon that overturns its entire surface every 400 to 600 days. A sea of molten rock the size of a US state, resurfacing itself on a schedule as regular as seasons. Io's surface is painted in yellows and oranges and whites and reds and blacks. The entire color palette of sulfur expressed across 1,000 different temperatures. It looks like a world that is digesting itself from the inside. And Io sits inside Jupiter's radiation belts, the most lethal electromagnetic environment in the solar system. The charged particles Jupiter concentrates fall on Io's surface with enough energy to strip away its thin atmosphere and alter its surface chemistry. A human on Io would receive a lethal radiation dose within hours, setting aside everything else: the volcanoes, the sulfur, the vacuum, the temperature extremes. Just the radiation alone is enough. Io is what Jupiter does when it grips something too tightly. It tears it open. It heats it until it bleeds. Jupiter broke a world to build a furnace, and it called it a moon. In 1979, Voyager 2 flew past a moon called Europa and sent back images that changed everything, though almost nobody realized it at the time. The images showed a surface of ice, brilliant white, almost completely smooth, nearly devoid of impact craters. And crossing that smooth white surface, thousands of dark reddish-brown lines, fractures. The ice was cracked. Something beneath the surface was moving, pressing upward, causing the shell to fracture and refreeze in new configurations. The smoothness said something immediately. Europa's surface is young, new. Something is continuously resurfacing it, erasing the impact record, replacing old ice with fresh. Something active was happening beneath that shell. Over the following decades, as the Galileo spacecraft orbited Jupiter and made repeated close flybys of Europa, the answer emerged. Jupiter's powerful magnetic field induces secondary magnetic fields in any electrically conductive material it passes through. And Europa was generating an induced magnetic field consistent with exactly one thing: a global layer of electrically conductive fluid beneath its surface. Salt water. A global ocean of liquid salt water wrapping the entire moon beneath an icy shell perhaps 15 to 25 kilometers thick. The volume estimates are staggering. Europa's subsurface ocean contains an estimated 2 to 3 times the volume of all of Earth's oceans combined. in a moon smaller than our own moon. More liquid water than exists anywhere else in the entire solar system, hidden under ice in the dark, warmed by the same tidal forces that tear Io apart, but gentler, just enough to keep water liquid, not enough to turn Europa into a furnace. And the water is salty. Sodium chloride, table salt, detected in the surface ice by the Hubble Space Telescope. The same mineral that makes Earth's oceans taste the way they do. The signature of water that has spent a long time in contact with rock. A rocky seafloor. Water against rock, with heat, over billions of years. That combination, water, rock, heat, time, is exactly what we believe produced life on Earth. In 2013, Hubble detected water vapor plumes erupting from Europa's southern polar region. Columns of water shooting 200 kilometers into space. Europa was venting its ocean, sending samples of its interior into the vacuum, where a spacecraft could fly through them and taste what was inside. I need you to take what I'm about to say seriously. There is a spacecraft flying right now that may answer the most important question a conscious species has ever asked. And on October 14th, 2024, a spacecraft launched from Cape Canaveral, Florida, to do exactly that. Europa Clipper, the largest planetary science spacecraft NASA has ever built, 6 meters wide with its solar panels extended, carrying 9 scientific instruments, cameras, spectrometers, a magnetometer, ice-penetrating radar capable of seeing 30 kilometers through the shell, and a mass spectrometer designed to detect complex organic molecules in any plumes it encounters. Europa Clipper is flying right now, as you read this, crossing the solar system. It will arrive at Jupiter in 2030 and conduct 49 close flybys of Europa, some passing within 25 kilometers of the surface. If plumes are active during any of those flybys, Europa Clipper will fly through them. It will taste what is in Europa's ocean. The scientists building toward this moment have been preparing for decades. Brittany Schmidt, a glaciologist at Cornell University, who studies how ice behaves on Earth and applies those lessons to Europa's shell, has described Europa as the destination her entire career has been pointed toward. She is in her 40s. She has been preparing since her 20s. She will be in her 50s when the primary data returns. Kevin Hand, an astrobiologist at NASA's Jet Propulsion Laboratory, has spent 20 years studying the chemical interactions between Europa's icy surface and the radiation from Jupiter. Specifically, how oxidants produced by radiation in the surface ice could be cycled into the ocean below, providing the chemical energy that life could exploit. He has built experiments, written models, made the case, paper by paper, that Europa's ocean has not just the right ingredients, but the right energy. He will be in his 60s when the data comes back. These are people who chose their careers, their graduate schools, their entire professional lives, around a question that will not be answered until they are older. Some of them, statistically, will not be alive to see the final results. They built toward something, knowing they might not reach it. That is the scale of what we are asking. And that is the kind of people who ask it. The question they are asking is this: is anything alive in Europa's ocean? Consider what we know. On Earth, hydrothermal vents at the bottom of the ocean. Dark, hot, mineral-rich environments with no sunlight and crushing pressure. Host entire ecosystems. Tube worms, shrimp, bacteria, archaea. Life that does not need the sun. Life sustained entirely by chemical energy from Earth's interior. We discovered these ecosystems in 1977. They shattered our understanding of where life can survive. Many scientists now believe life on Earth may have originated at hydrothermal vents, that the first cells were born in hot, mineral-rich water at the bottom of a dark ocean billions of years ago. Europa almost certainly has hydrothermal vents. It has a rocky sea floor in contact with a warm ocean. It has the chemistry. It has the energy. It has had billions of years. And Jupiter, the same Jupiter whose radiation is lethal at Europa's surface, is actually feeding whatever might be in the ocean below. Charged particles from Jupiter's radiation belts strike the surface ice and drive chemical reactions that produce oxidants. Hydrogen peroxide, oxygen, sulfate compounds. These oxidants can be cycled into the ocean through ice, dynamics, and plume venting, providing the chemical energy gradient that life can exploit. The same gradient that powers deep-sea ecosystems on Earth. Jupiter is poisoning Europa's surface, and in doing so, it may be feeding Europa's ocean, the destroyer providing for what it cannot reach. If Europa Clipper's instruments detect complex organic molecules with chemical structures that cannot be explained by geology alone, patterns that look like biology, that carry the fingerprints of something metabolizing, something processing energy, something alive, it will be the most significant discovery in human history. Not among the most significant, the most significant, by a margin that is difficult to overstate. Because it would mean life on Earth is not a miracle, not a lucky accident. It would mean life is something the universe does, a process that emerges wherever conditions are favorable. And the universe is extraordinarily large, and there are many places where conditions resemble Europa's. It would mean we are not alone, and never have been. If Europa Clipper finds nothing, if the ocean is sterile, the chemistry purely geological, no hint of biology in the plumes, that answer matters too. It would mean that even when all the conditions are perfect, even when water and heat and chemistry and time all align, life does not always begin. The barrier is higher than we thought. The universe can build the most elaborate possible stage and still have no performance. Both answers are real. Both will change us, and neither will leave us where we are now. Europa Clipper is carrying both possibilities right now, crossing the solar system in the dark. And the people who built it are waiting. One thing before we leave Jupiter's moons. Ganymede is the largest moon in the solar system, larger than Mercury, larger than Pluto. If it orbited the Sun instead of Jupiter, we would call it a planet without a second thought. And Ganymede has its own magnetic field, generated by its own metallic iron core, warm enough, active enough, to sustain the dynamo that Earth and Jupiter have. Ganymede has carved out a miniature magnetosphere inside Jupiter's enormous one. The Hubble Space Telescope has detected Ganymede's own auroras, ribbons of light in its thin atmosphere, generated by charged particles interacting with its own magnetic field. Auroras on a moon. And Ganymede has a subsurface ocean containing more liquid water than all of Earth's oceans combined. 3 times more. Beneath perhaps 800 kilometers of ice, an ocean perhaps 800 kilometers deep. Europa has an ocean. Ganymede has an ocean. Callisto, the outermost large moon, probably has an ocean. Enceladus around Saturn has an ocean. Titan may have one. What we are discovering, world by world, flyby by flyby, is this. Liquid water oceans hidden beneath ice are not rare exceptions in the outer solar system. They may be the rule. We built our entire search for life around the habitable zone, that narrow band of distance from a star where liquid water can exist on a surface. Earth is in it. Mars barely. Venus barely outside. Jupiter's moons just told us the framework was too small. Tidal heating, a massive planet needing its moons, can maintain liquid water oceans at distances from the Sun where nothing should be liquid. Any massive planet, anywhere in the galaxy, orbited by icy moons, might be keeping those moons warm, might be maintaining oceans in the dark, might be creating conditions for something to begin. Jupiter did not just reshape our solar system. It reshaped our understanding of where to look in the universe. We began with a deal. Jupiter absorbs impacts. We live. Let us be precise about the cost and honest about what the deal actually is. In the early solar system, during the period called the Late Heavy Bombardment, the impact rate on rocky inner planets was thousands of times higher than today. Comets falling inward from the outer reaches. Asteroids stirred from stable orbits. A constant rain of space debris resurfacing every rocky world in the inner solar system multiple times in the first billion years. Jupiter was responsible for much of this chaos. Its migration through the early solar system scattered material inward. Its gravitational resonance with Saturn destabilized the outer solar system and sent thousands of icy bodies toward the Sun. The bombardment that scarred the Moon so thoroughly that those craters are still visible today. Jupiter helped cause that. But those same icy impactors delivered water to Earth, delivered organic molecules, the carbon-containing compounds that became the building blocks of life's chemistry. The bombardment was catastrophic. The bombardment also built the foundation. Jupiter caused the disaster. The disaster made us possible. And since the bombardment, Jupiter has continued its role. Its gravity deflects a significant fraction of objects that might otherwise reach the inner solar system, sending them into orbits that carry them away. It also, occasionally, stirs objects toward us. The balance is not perfect. The protection is not complete. Jupiter is not a shield. It is a gravitational condition, indifferent, ancient, enormous, and statistically, historically, more favorable to our existence than our absence. The comet Shoemaker Levy 9, the one Carolyn found, the one Jean co-discovered, the one that struck Jupiter in 21 fragments with the energy of 300 times all human nuclear weapons. That comet was not aimed at Earth. We cannot say with certainty that Jupiter caught it for us, but we can say that without Jupiter, the dynamics of this solar system are different. The impact rate is different. The history is different. We are not just a lucky planet. We are a lucky arrangement of an entire system. And Jupiter is the largest piece of that arrangement. Gene Shoemaker spent his career understanding impact craters, what they meant, how they formed, what they told us about the history of the solar system. He studied them on Earth. He helped train the Apollo astronauts to recognize them on the Moon. He co-discovered the comet that became the most spectacular planetary impact ever witnessed by human beings. And he died before seeing where that discovery led. Before the plumes of Europa, before the confirmed ocean, before Europa Clipper was even a funded mission. He gave everything to understanding what Jupiter is. The condition existed before he did. It will exist long after everyone who remembers him is gone. That is the deal. That is what it costs. That is what it gives. Europa Clipper is flying through the dark right now. Not a metaphor. Not a figure of speech. A spacecraft built by thousands of people over 2 decades, launched in October 2024, is crossing the solar system at this moment. Signals from it travel at the speed of light and take up to 52 minutes to reach Earth from Jupiter's distance. Someone at NASA's Jet Propulsion Laboratory is looking at data from Europa Clipper on a screen right now, confirming it is alive, confirming it is on course. It will arrive in 2030. It will begin 49 close flybys of Europa, and in the data it sends back, in the chemical signatures of its spectrometers, in the radar returns from beneath the ice, in whatever it tastes when it passes through a plume, there will be evidence bearing on the most important question a conscious species can ask. Are we alone? Not the philosophical version of that question, the one humans have carried for thousands of years without hope of evidence. The empirical version, the one with a spacecraft, the one with instruments, the one that will produce data that scientists will analyze and debate, and eventually, gradually, carefully, reach a conclusion about. There are 2 ends of the possibility space. At one end, evidence of life, not creatures, microbes, chemical signatures with the fingerprints of biology, organic molecules in ratios and structures that geology alone does not produce, isotopic patterns that suggest something is selectively processing chemistry, the way all living things do. If that evidence comes back, it will take years to confirm. It will be contested. It will require more missions. But it will begin the process of answering whether life on Earth is unique, or whether life is what the universe does whenever conditions allow. It would mean we are not alone. And it would mean we never were. And the question changes from whether there is life elsewhere to how much life there is, and where, and what it is like, and whether any of it has ever looked up at its own sky and wondered the same thing we have wondered about ours. At the other end, silence. An ocean that is chemically rich, geologically active, perhaps surprising in its composition, but sterile. No fingerprints of biology. A place where all the ingredients assembled, where the conditions were right, where billions of years elapsed, and nothing began. That answer is harder to hold. It would not close the question entirely. There are other oceans, other moons, other solar systems. But it would mean the barrier to life is higher than we thought. That conditions being right is necessary, but not sufficient. That the universe can build the most elaborate possible stage. Liquid water, heat, chemistry, energy, time, and the performance still may not begin. Both answers are real. Both will change us. And we are the first generation in human history that is not simply waiting in the dark for an answer. We are the generation that built something and sent it there. Carolyn Shoemaker sat in a telescope dome in California in 1993 and found a smear of light on a photographic plate. She did not know what it was yet. She called her husband. She looked again. She was careful. She was patient. She had spent decades learning to see what other people missed. And what she saw, in the end, was Jupiter doing what Jupiter has always done, absorbing, reshaping, deciding, without intention, without awareness, without any knowledge, that down in the inner solar system, on a small, rocky peppercorn of a planet, there were creatures who had built telescopes and learned to look back. We are those creatures. And we have looked. And we have seen what Jupiter actually is. Not a bright dot in the night sky. Not a piece of ancient mythology. Not a decoration in an astronomy textbook. A condition. The condition under which this solar system stabilized enough for Earth to hold water, for water to become oceans, for oceans to become chemistry, for chemistry to become something that eventually built a spacecraft and aimed it at a moon 1 billion kilometers away. Jupiter did not do this for us. It did not do this at all, in any meaningful sense of the word do. It simply is what it is. And what it is happens to include us. Look up tonight and find it. The brightest steady light in the sky, slightly golden, unwavering. Every human being who has ever lived has seen that light. Every civilization, every philosopher who ever asked why we are here, every astronomer who ever wondered if we are alone, every child who has ever lain on their back in the dark and looked up and felt something enormous and nameless. They all saw Jupiter. None of them knew about Europa. None of them knew about the ocean beneath the ice, the hydrothermal vents on the rocky seafloor, the tidal forces keeping it liquid, the plumes venting into space, the spacecraft we built to taste them. We know. And we built something. And we sent it. And it is flying right now in the dark, carrying the question that every conscious being in human history has carried, carrying it toward the place where the answer might be waiting. In the dark water beneath the ice of a small moon, near a hydrothermal vent on a rocky sea floor that has never seen sunlight, in an ocean warmed by the gravity of the most powerful planet in the solar system. Something might be swimming, and because of what we built, and where we aimed it, and what we dared to ask, we are going to find out. And when we do, whatever the answer is, nothing about that golden light in the sky will ever look the same again.